Hey guys, it's showtime. Good morning. First of all, heartfelt thank you for coming so early in the morning to this session. My name is Tarique Shakil, and I'm a principal engineer for the product management for Cisco Nexus 9000 NXOS. With me,
And I am Shankar Gopalkrishnan. I'm a principal engineer in the development team engineering.
Right, so we welcome you to this session, Secure Network Infrastructure in VXLAN BGP EVPN Data Center Fabrics. I'm sure a lot of you read the abstract, right? And what we need to really understand is, what do we mean by secure network infrastructure? Network security is a very vast field, right? And what our focus of this session is to educate you on the best practices of securing the switch itself, so that the switch can perform its most fundamental function, which is to forward packets. You can have the most fanciest firewall in the entire world, but if the switch doesn't have integrity in its forwarding table, a MAC table or IP table, to make the decision to even forward a packet, you lose complete network connectivity, right? So we're going down to the fundamentals of network infrastructure security. The agenda is, first we're going to give you an overview of VXLAN BGP EVPN data center architecture. Now this is an advanced session. I assume you already know VXLAN BGP EVPN. But what we need to do is put on our security glasses and look at the infrastructure and ask ourselves, what are the considerations I need to have in my mind? What are the questions to understand how do I harden this infrastructure at its various layers? So that's what we're going to discuss briefly. Then we're going to look at the various security challenges that we can experience in the VXLAN BGP EVPN data center and all these layers, and how do we mitigate them. We've grouped them into 3 areas: endpoint protection, data plane protection, and control plane protection. And then we summarize. This will be a little bit of a roller coaster, some advanced topics, very deep, and then slow it down, and then, all right, so packet walks will be there, how the system works, right? So let's start off with the VXLAN BGP EVPN data center architecture. VXLAN is the data plane protocol. So its job is to extend layer 2 over an IP fabric. Right? So we have the underlay and then we have the overlay. 2 things that we need to consider. First, VXLAN extends your layer 2. In effect, it's extending your bridge domain. And because you extend your bridge domain, you have the ability to have host mobility. So hosts are moving in your data center. So now you need to think, as a security guy, hosts are going from VTAP 1 to VTAP 2. So whatever configuration I apply in VTAP 1 for that specific host, whatever security policy I applied, whatever state that was there to enforce my security, it should also follow the host to go to the destination VTAP, right? First thing. Second thing is, as you extend your bridge domain, you extend your, it starts with F, flooding domain, right? And F, flooding, actually could possibly equate to another word that starts with F, which is failure domain, right? Because you can extend the blast of any sort of storm across your fabric. So it's nice that we can have host mobility, but then you have a side effect, which is you also extend your flooding domain. And we don't want floods to get out of control, especially if you have floods with loops, right? That has a multiplier effect then. So we're going to address both of those things. Sorry, one last thing. One other aspect, we told you about host mobility. The other aspect is VXLAN allows you to have a scale-out architecture. So what does that mean? As we keep adding switches, it's very flexible. Great. We can scale out whenever we need to add more hosts. We add another spine. We get more capacity for east-west traffic. But as you add more switches, you add more state, right? Configuration state, policy state, network state, right? So now you need to think in your mind, the way you address security, yes, we have convenience, but we have to balance convenience with security, right? As you scale out and you scale up by adding spines, we need to think, okay, how do we ensure, as we're adding more of these in systems, how is our state, how do we maintain the health of the security as the fabric grows? So we're going to look at these concepts as we proceed. The other aspect of VXLAN, which is fundamental to security, is that it provides segmentation. So when we had VLANs, first we had normal switches, then we decided that we needed to connect HR and finance, but we didn't want them to talk to each other, so we created VLANs for them, right? But then we had multi-layer switching. Now we had ability to route in these switches, but all the VLANs were in the same network, so then what did? We created virtual routing tables with VRFs. We retained that segmentation with VXLAN through L2 and L3 VNIs, right? So a VLAN maps to an L2 VNI, which maps to a bridge domain, and then you have multiple L2 VNIs within a VRF, that's within a routing table. What is that providing us? Segmentation in the data plane. We're isolating traffic in the data plane. So that is fundamental to security, right? What do we do as security professionals when we are trying to analyze the network? We're classifying our users, we're classifying our applications, and then we're saying, okay, who has access to what? And we group them. And the first thing that we group is VLANs and networks. So VXLAN, by default, is already providing you the segmentation, right, at the data plane. Now we need to retain the segmentation in the control plane. So as you're implementing the VLANs, as you're implementing the VRFs on your VTAPs, we need connectivity across this layer 3 fabric. So we need a protocol that can exchange MAC information, that can exchange IP information, while at the same time exchange tenancy information. We have a virtualized multi-tenant system, and that's what MPBGP EVPN's role is. It ensures that the tenancy information exchange between edge devices is retained through the route distinguishers and route targets, right? We always use those old tools that always work from the box, right? And we brought it over into the data center. So again, here's the key word. We're segmenting in the control plane, we're segmenting in the data plane, and that's foundational to security, and VXLAN does that well. Lastly, if we look at VXLAN, we actually have 2 layers of networking occurring. We have the underlay, and the underlay is running its networking services, OSPF, IS, BGP, PIM, or we can do ingress replication. Right? Now, what's the job of the underlay? Tap-to-tap reachability. If the underlay breaks, what happens? No tap-to-tap reachability, overlay connectivity broken. So we need to consider that we need to manage, operate, troubleshoot, and secure both the underlay and the overlay. So we need a multi-layered approach when we look at securing the VXLAN BGP EVPN infrastructure. So basically what happens, the underlay and overlay is the attack vector for any threat actor. So now I'm going to spell out and discuss and outline for you some of the challenges areas that we're going to look at. The first challenge area we're going to look at is endpoint, securing your endpoints. Your endpoints are part of your overlay, right? So we want to make sure we control who connects. Only authorized endpoints connect to my overlay network. And we do that through DHCP snooping, dynamic ARP inspection, IP source guard. But you've probably heard all this before, right? But how has things changed in VXLAN EVPN? Because now we have hosts moving everywhere. How do we retain that snooping database? So we'll teach you how that works. Then we're going to look at data plane. Data plane is a vast topic itself. We're going to look at various areas, storm control, loop detection. We're going to prevent DDoS attacks with BGP, EVPN, remote traffic blackholing. Again, old tools from the SP world brought into the data center. Then MACsec, ensuring confidentiality of data as you're sending it out through your fabric, hop by hop. And the last thing we're going to look at is protecting your control plane, your CPU. That is the most important resource of a network system, because the moment the CPU has no resource to process any packet, any control plane packet, your data plane is going to be out of sync, right? It's not going to have that integrity that you need. So now I'll hand it over to my friend Shankar, who will now walk you through endpoint security.
Thanks, Tarique, for setting the context and getting us to this point. So I was telling Tarique yesterday, when I get in front of this audience, I want to start with a quote from a film, right, a movie, just so that I don't bore this audience. And I was thinking about it as to what would be the right one for it. And it immediately clicked. The Godfather is the sum of all wisdom. The Godfather as the answer to every question. What day of the week is it? Monday, Tuesday, Thursday, Wednesday. It is Thursday. Welcome to this session, and welcome to endpoint protection mechanisms. Yeah, so as Tarique explained, we are going to take it in 3 fronts, right? He talked about endpoint protection, data plane protection, and control plane protection. I'm going to talk about endpoint protection mechanisms. So what do we mean by endpoint protection mechanisms? The endpoint is the same as the host, the client, right? So why do we need to protect the endpoint of the host? Because the entire data center, after all, exists for the host, and hence it makes sense to start with protection for the endpoint. So here in this section, we are going to talk about 3 related features we are all familiar with. The dynamic host control protocol snooping, and then we're going to talk about dynamic ARP inspection, DI, and we're going to talk about IP source guard, IPSG, right? All these features we are familiar with, right? What we're going to do right now is to go through a primer for each one of them, just to refresh ourselves as to what these features are all about. And having set the context with the primer, we are going to see as to how we implemented these features in a VXLAN context and what challenges were brought in bringing these features into VXLAN. So that's the format we are going to be following. A primer for each of these features to see as to how they play a role in terms of taking up security issues, and then dive into VXLAN to see as to how we had to factor in certain unique peculiarities in VXLAN to bring these features to fruition. With that, one last point in terms of the terms that we're using. Endpoint protection is the same as host protection, is the same as client protection, application protection, whatever you may want to call it. And more importantly, it is what we call as overlay protection, what Tarique mentioned. That has to be taken care. So DHCP snooping, what problem does it solve? So as the scroll out here says, DHCP snooping prevents a rogue DHCP server from assigning a compromised, meaning a bad address to a host. A compromised IP address, what will it do? We all know it'll lead the traffic from the host to be diverted to the rogue server, something that we don't want, obviously. Yeah, so let's now get to the basics to see as to what the feature is. This is just a primer of sorts, and then we will see as to how it works in VXLAN. So when we talk about DORA, what does it mean? DORA is the method through which a host gets its IP address from a DHCP server. As soon as a host comes up, one of the first things it does is to get the IP address. I'm sure we are all familiar with it. But DORA stands for the sequence of messages: discover, offer, request, and acknowledgement. So how does that happen? The host says, you know what? I need an IP address. And it doesn't know as to where the DHCP server is. It just knows that the server is in the same subnet, right? So it sends a broadcast message, the DHCP discover, saying that, you know what? I need an IP address. And the DHCP server in that subnet says, here you go. This is the offer I'm making. This is your IP address. Thereafter, the host says, it sends a request message in which it says, I will go with you. Why does it say that? Because you can have multiple DHCP servers in your subnet. So the host has to sign up with one of them, and it does that through the request. And finally, the server replies with the acknowledgement, and the DORA transaction is complete. And what have we achieved through it? Yes, of course, we got the IP address from the DHCP server, and the host now has the IP address. Of course, we are familiar with this. What is a security loophole in DHCP? We'll just go through that as well, set the context. The DORA message, as we saw, the discover, is a broadcast message. It comes to the switch. The switch sends it everywhere in the L2 domain. It does go to the rogue DHCP server as well. We cannot prevent that, of course. And it goes to the legitimate DHCP server. And then what happens? The DHCP server replies with an offer, right? He does it even before the legitimate server does. He says, I'm going to make you an offer that you cannot refuse. Anyone as to where that line is from? The Godfather. Yes, so he sends an offer, and the host cannot refuse that because it went to him first, right? And then the second offer goes from the legitimate server, but because the host signed up with a rogue DHCP server, what happens? The transaction is now, the DORA transaction that we talked about, is complete between the host and the rogue server. And what is the end result? The rogue says, you know what? I just assigned a bad IP address to you, host A, and now not just your IP address, the gateway IP, which was given to you as part of the offer message, that is also compromised. It's my address, the rogue says. And what is the end result of this whole thing? The next routed packet from the host, right? Instead of going to the network, it goes to the rogue DHCP server because the gateway IP is his. So that is a compromise that happens. So how does DHCP snooping help? Again, we just go through the primer, and then we dive into VXLAN. Don't worry, I'll get there. Yeah, so when we talk about DHCP snooping, we turn the feature on the switch, the one in the center. What are you supposed to do with this feature? You're supposed to configure certain interfaces as trusted. In this case, the switch configured the trusted interface facing the DHCP server. All the other interfaces were left untouched. That means they are untrusted. What happens with this configuration? The discover message, like the last time from the host, came to the switch. The switch will not forward that to the rogue DHCP server because it's an untrusted interface, right? So he has snooped the discover message and ensured that it goes only to a trusted interface and never to an untrusted interface. So do not forward the discover. It is an untrusted interface. And thereafter, it goes to the DHCP server because it's trusted. The server replies with the offer, which is good. And the offer is also snooped to ensure that it came from a legitimate, a trusted port. So that also is taken care by the switch because you turn the DHCP snooping on. And it goes all the way to the host, and then the transaction for DORA is now complete only between the DHCP legitimate server and the host. At the end of this entire exercise, what happens on the switch? We have a DHCP snooping database formed. And what does it contain? It has the MAC of the host with which it started the discover. It also has the IP address which was assigned by the DHCP server, and certain other parameters like lease time we'll get into shortly. But this database gets formed on the switch, right? And one last point, what if an unsolicited offer comes from the rogue switch? Even in that case, because I've turned on the DHCP snooping feature on the switch, it does not take up the offer because it came on an untrusted interface. So that's the advantage of having this, saying that, you know what, now no more diversion to the rogue DHCP server, which was there in the first place. Yeah? We have prevented that. Okay, all this is fine. How does it fit into VXLAN, right? So that is what we are going to see right now. With that context set, now if you look at this picture in VXLAN, we have to map it to the primer. What is the difference between the two? Here you can have the host and the DHCP server far apart, right? The host A is on VTEP 1. The DHCP server is on a completely different VTEP in the VXLAN fabric. It could be even in another fabric in case of the multi-site case, right? So that's why they are far apart, and now this feature needs to work in this kind of topology. So as usual, interfaces have to be configured as trusted and untrusted, right? So what does it mean? The DHCP snooping feature has to be turned on in the entire fabric on all the leaf VTEPs, right? In addition, you have to configure the interfaces as trusted on those VTEPs where you have a legitimate DHCP server as shown in green, right? So that is what you need to do in a VXLAN context to make this feature work. The discover message, remember DORA? It came from the host. It comes to the first switch, which is VTEP 1. What does VTEP 1 do? Remember, it has DHCP snooping configured. It should send it only on the trusted interface. So here is where the peculiarity of VXLAN comes in. You need to have the entire fabric, the NVE interface as we call it, as an implicitly trusted interface so that you can allow the transaction of DORA to go across the entire VXLAN fabric. So that's what VTEP 1 has done. It forwarded it to the spine. What did the spine do? It has to forward it to all the VTEPs which have their VLANs configured with this. So it goes to VTEP 2. What does VTEP 2 do? It has a DHCP snooping feature configured. And like we saw in the primer, in this case, VTEP 2 will not forward the discover message to the rogue because it's an untrusted interface, right? Do not forward it. And thereafter, the discover message comes to VTEP 3. And what did VTEP 3 do? It forwarded the discover message to the DHCP server because it's a trusted interface. So you have to take care of all that in the VXLAN context by punting the discover packet up to the VTEP, and then it has to decide on which interfaces it has to send this to. And mind you, it need not be a single interface because you can have multiple DHCP servers. So every VTEP should have the capability to be able to send the discover message possibly to multiple trusted interfaces, right? So all that has to come in when we implement this feature in VXLAN, and that's where the challenge in this particular feature is, right? So now that that is done, the offer comes from the DHCP server. And what does VTEP 3 do? It snoops the packet, ensures that the offer has come from a trusted interface, and only after that it forwards it over the VXLAN fabric. The offer comes all the way back, as it should, and the request comes from host A, and it goes all the way back to the DHCP server. The acknowledgement comes from the DHCP server, and at the end of it, DORA transaction is complete. Our host got its IP address from the DHCP server, even though they were far apart, unlike the primer. And at the end of it all, the DHCP snooping database gets formed. And where is it formed? That's the important point. It got formed on only VTEP 1 because that is the switch which faces the host. We will see as to what it means in having it only there. At this point, we just want you to appreciate that the DHCP snooping database comprising the MAC and the IP which was involved in this DORA transaction, that got formed only on VTEP 1, right? And we go forward. So what is the takeaway from this? We say that the DHCP snooping ensures that a secure IP address is given to the host from a trusted DHCP server. And then we make a point to say that, you know what? The DHCP snooping database also gets formed on the host VTEP. And why is this important? As we will see, the other features we are going to talk about, dynamic ARP inspection and IP source guard, are going to use this particular table, right? Yeah. So before we go forward, just a few things in terms of configuration. You have to turn, of course, the feature on, the feature DHCP. You have a global level command to enable the feature. And then on those VLANs where you want this particular feature, you enable that by doing the step 3, which is the snooping VLAN with the EVPN keyword because it has to work in a VXLAN context. And finally, in step 4, we show as to how do you configure an interface to be trusted. So that's the 4th command. And as it says out here, there's a particular sequence in which you need to do this. That's OK. You do it at the global level and then at the VLAN. That's fine. But the last one is the most important thing in terms of you need to have this configured on all the leaf VTEPs of your fabric for this feature to work seamlessly in a VXLAN setup. Right? Global config, VLAN config, and then how to configure the trusted interface. We saw that, and then we go on to the next one, which is, remember the little box we saw on the host VTEP, which was the DHCP snooping database. What does it comprise of? So here's a CLI command for that. So it has the host MAC, of course, which started the DORA handshake. It has the IP address, which got assigned from the DHCP server, right? So we have that. And then the host VLAN on which the host is on, and the host interface, of course. And the lease time is something we will get to very shortly. But it says that the DHCP server tells the host saying that thou shalt use this particular IP address for this much time. So that's the lease time. And finally, we have a command to say, you know what, if I want to see all the VLANs on which I've enabled this blessed feature, how can I do that? And there's a command to show that as well. So with that, we come to the finish of the first of the 3 endpoint features, DHCP snooping. Now we are going to get to the second one, dynamic ARP inspection, a very related feature, and we'll be following exactly the same pattern. We will look at the primer just to refresh ourselves, although we all know about it. And then we will dive into what it means in the VXLAN context. So the same procedure out here. Dynamic ARP inspection, what problem does it solve? Right? You can have spurious ARP or gratuitous ARP messages sent by an attacker, right? So he kind of pounds with ARP requests with different MAC and IP combinations, and thereby he poisons the ARP cache on the switch. He can do that, or he can cause a man-in-the-middle attack. We'll see as to how that happens. So this animation is all about that. So what happens in this case? Host A sends out an ARP request. What does he send it for? He wants the MAC address of the server which has this IPB, right? So that's the reason why he's sending the ARP request, yeah? So the ARP request is a broadcast packet. So because it's broadcast, it will be sent to everyone in the L2 domain. It will reach the attacker as well. You cannot prevent that, of course. It goes to server B also. And now what happens? Like in the previous case, the attacker wakes up and says, you know what, I'm going to send you an ARP reply. And how does he send the ARP reply? He says that, you know what, I am IPB, right? He masquerades as the server B, and he sends his MAC, right, which is MAC C, saying that this is the reply I'm giving, right? So that is what the attacker did. So what was the end result? Host A has no way of confirming that this is a bad value. He goes with that, and the next bridged packet, which the host intended to send to the server B, ended up coming to the attacker, right? So this is, again, a huge problem, right? So the attacker has successfully diverted the host A's traffic destined to server B to himself by being a man in the middle. So we all know about this. We'll just see as to how we take care of this problem in dynamic ARP inspection. Yeah, again, the primer. So what do we do in that? First and foremost, for dynamic ARP inspection to work, we need DHCP snooping, what we just finished, right? And what happens with that? You rely on the database that you created after DORA. Like DHCP snooping, you're going to turn on DI also on the switch. On the switch, we have the DHCP snooping DB. In this case, it's populated with the entries of host A as well as server B. Their MAC IP combinations derived through DORA are present in this database. So what happens with this? Right? So now, when the host A sends the ARP request, so because you turn the DI feature on, dynamic ARP inspection on, this particular ARP request will be snooped, and we will check as to whether its credentials match with the entries that we have in the snooping database. And if it matches, only if it matches, I'm going to forward that beyond this point, right? So it says good to go, and because it's matching with the snooping DB, and then he forwards the ARP, right? And it does go to the attacker as well, but that's not a problem per se. And now, like the last time, the attacker wakes up and says, I'm going to spoof a reply, right? And he does the same thing as what he did earlier. He says, I'm IPB, and it's MAC C. So now what happens? Because you turned on dynamic ARP inspection, you're going to look at this packet to see as to whether the source credentials in the ARP reply match with the database that you have. In this case, it will not match because IPB MAC-C is not a valid combination which was got through DORA. So he suppresses, blocks that particular ARP reply, which is very good, right? And now when the legitimate ARP reply comes, there's no problem at all, right? It goes all the way because the matching is there in the snooping database. It goes back to the host, and DAI has successfully solved the spurious ARP reply problem. Yeah. So now, having looked at the primer, hope you're all with me. We are going to look at how this dynamic ARP inspection works in a VXLAN context. Again, the picture is the same. We have the host A on one side, and we have the server on the other. After DORA exchange, right, what we just looked at in case of DHCP snooping, what did we see? It's the same thing, saying that I have the snooping database. This is what we looked at in the DHCP snooping feature, is populated with the IP and the MAC address of host A, right? And so when the next ARP request from the host comes, or a gratuitous ARP, we are going to look at the credentials of the ARP and then check against the snooping database to confirm that there is a match. Only if there is a match, we are going to forward it, right? So that's why it says a green tick out there saying that it matches. What if the host moves? So why are we talking about host move? As Tarique said, this is one of the behavioral patterns in VXLAN we have to contend with. Of course, we all know that VXLAN move is a distinct possibility. So in this particular case, what happens with host move? The host moves, right, to VTEP2 from VTEP1. It now sends the same ARP request or gratuitous ARP. The DAI feature, like the previous case, has to be turned on every VTEP because we want that, right? So now what happens? He tries to match his credentials, the source credentials, with the snooping DB. But your snooping database is empty. Why is it empty? Because after DORA exchange, it got populated on only that VTEP which faced the host, right? So that's why it's empty on VTEP2 as well as on VTEP3. So host mobility will be a problem if you do it the traditional way for dynamic ARP inspection or any other feature involving a move in case of VXLAN. So what do we do about it? So it says out here, DAI fails. What next? For DAI to succeed, this is the $1 million point, saying that for DAI to succeed after a host move, the snooping database needs to be replicated across the entire fabric. The question is, how are we going to do that? For that, we take recourse to the control plane in VXLAN, BGP EVPN route type 12. Right? So that's the new one we're going to talk about here. We all know about type 2 to send MAC and MAC IP information in the network. Yeah, we are familiar with that. We are also familiar with type 5, which advertises prefixes. Just like that, we have route type 12, which is used for this purpose, meaning it is used in order to transport the DHCP snooping credentials, right, all the way to the entire fabric so that it can be populated on the different VTEPs. There is a standard for it, as we see out here, and some information related to that. But the content is what we need to look at. What is the content of route type 12? It should have the MAC, yes. It should have the IP address. It should have the lease time because it came from the DHCP server. I need to retain that. It also has something called create time, the time when DORA got completed, which we will see a little later as to what it means. Right, so now, the breakup of route type 12, we are going to cover it in one of the other slides, so just hold on for now. We'll now see as to how this works. We wanted this entry to be populated across the fabric, correct? This is how it happens. After DORA, just like the last time, it's populated only on VTEP 1, right? This is how we saw it. Now route type 12 will kick in. What does it do? It sends the information to the spine reflects it to all the other leaves, and voila, it got populated on VTEP 2. And it went to VTEP 3, and yes, it got populated out there too. And now the entire fabric has the DHCP snooping entry for host A in the entire fabric, which was originally only on VTEP 1, has now reached everywhere because of BGP EVPN route type 12, right? So now what happens? The coast is clear for a host move. We'll just see that as to how it happens. The last time the host moved, dynamic ARP inspection, remember, it could not be performed because the snooping database was empty. But now, because of BGP EVPN route type 12, it has now spread over the entire fabric. So now, when the host sends the ARP request or a gratuitous ARP with its credentials, it matches the DHCP snooping database, as simple as that. And now you're good to go. Yeah? We'll now see how this takes care of attacks as well. So how does it look? It's the same picture. It's just populated with 2 entries corresponding to host A and host B. Nothing different about this picture from the previous one, except that it has got populated in the entire fabric with BGP EVPN route type 12. Yeah, it's just setting the context for that, saying, I know about the information of host A and host B after this. The attacker, right, before that, the host A sends the information, a proper ARP request, no problem at all, DI will succeed. And it goes all the way because it's an ARP request. Yeah, so ARP request is a broadcast packet, and it'll go across the entire fabric. It'll reach host B. Now, like the last time, we have the attacker waking up and saying that, you know what, I'm going to spoof a reply, a bogus reply, a compromised reply that we saw in the primer. It's the same issue out here. So what happens with that? He uses the same credentials. IMIP-B, he masquerades, and then he sends MAC-C. But in this particular case, nice try, it doesn't succeed. Why doesn't it succeed? Because the ARP reply, when it came to the VTEP 2, it found that there was no match at all. So regardless of where the attacker is placed, because of the way we have replicated this DB across the entire VXLAN fabric, we can prevent attacks of this kind from anywhere in the fabric. And now when the reply comes from the legitimate host, no problem. We will check against the snooping DB, and it'll go all the way to the destination. So dynamic ARP inspection helps to protect man-in-the-middle attacks in a traditional network, as we saw in the primer, as well as in our blessed VXLAN fabric. DI configuration, something very simple. First and foremost, have DHCP snooping feature configured. Why is that needed? Of course, we need that database. That's why we're going to do that. And then you enable this feature on every VTEP on a particular VLAN, because like DHCP snooping, this is also a VLAN level feature, right? So you enable it there. And of course, it has to be in all the leaf VTEPs. We've said that. One little point in terms of how the database looks. Remember, there is a host VTEP we talked about. We also talked about BGP EVPN route type 12 and how it downloads and populates it in the other VTEPs. So is there a difference in terms of how the database looks? A little difference is there. If you look at the first one, the host VTEP will have the explicit interface because it's facing the host. But on any other VTEP, because it got populated with route type 12, Ethernet 1/19 doesn't mean anything on those remote VTEPs, and hence it'll show up with the NVE interface and the peer ID of the host VTEP. That's about the only difference. So we go to the next one. How does route type 12 look? Like we said, yeah, so this is the host MAC. It has a host IP. It has a start time, the least start time when DORA got completed. It has a least duration. Yeah, so this is how the contents look. So all this is fine, but this is about control plane, right? Because dynamic ARP inspection is all about keeping your control plane safe. How about the data plane? How do we ensure that endpoints or overlay protection is there for the data packets as well? So that's where IP source guard IPSG fits in. We go into that next. So we've covered 2 of the 3. We talked about DHCP snooping first, then we talked about dynamic ARP inspection, and now we are going to talk about the third and the last topic in this particular content called IP source guard, right? Again, the same methodology. We're going to look at the primer just to set the context. So how does a primer look? We all know about this, saying that, you know, in IP source guard, there's again our attacker who spoofs an IP address, right? So you have the attacker in red. He says that, you know what, I am the victim, 10.1.1.50, which isn't him, and then he sends packets with that. There's no one to police that, and then, you know, hell breaks loose because he gains unauthorized network access. And how do you solve the problem? Same method as the previous case with some small differences. You need to have DHCP snooping database because that is the holy grail. And then you download the DHCP snooping database to hardware. This is the most important point for IPSG, right? Because we said IP source guard is about protecting your data plane packets. So DHCP snooping DB, which helped you in validating ARPs, was on the control plane. You cannot use the same method for IPSG. You have to download the contents of the same database down to hardware so that the data packets can be matched against that. So it says, allows the data packet if the contents match the DHCP snooping DB in hardware, right? So that's the most important point about IPSG. And now we see as to how it works in a VXLAN context. So IPSG in VXLAN. So how does it look? First and foremost, the same thing. You need to have DHCP snooping enabled on all your leaf switches. And with that, what happens? Just like we saw BGP, EVPN, route type 12, blah, 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 all that, and the DHCP snooping database is present on all the leaf VTEPs. So far, so good. Now you turn on IPSG on each of those VTEPs. What happens with that? That yellow sticky is the important point, saying that, you know what? The same database which was available to you on the CPU and which you use for dynamic ARP inspection, download that down to hardware so that it's available for use. And with that, the next data packet which comes from the host, this is what we want to do, right? You want to check the credentials of every data packet, the source information, to ensure that it's proper. And IPSG succeeds because it matches the DHCP snooping credentials. What happens if you have an attacker? He can attack from any place. He sends a packet with a different combination. He uses someone else's IP A, and he uses his MAC. It fails because it doesn't match in the DHCP snooping database and hardware. So now IPSG has to work with a host move as well. Does it? Of course, because we have the database populated in hardware across the entire fabric. So now when you have a host move, no problem. You will send a data packet. You will match that against the database downloaded in hardware. The match succeeds. The source credentials of hosts, it matches. And now the data plane is also safe. What are the commands to configure IPSG? You first enable DHCP snooping because that's the most important thing. That's how you get your database in the first place. And then on a per interface basis, you kind of enable this feature saying that on these interfaces, I choose to turn IPSG on, which would be all the access interfaces on that particular VTEP. And like the last time, you need to do it on all the leaf VTEPs because you need to take host moves into consideration. So you cannot localize it to a particular VTEP when you talk about VXLAN. IPSG commands, as to, tell me those interfaces as to whether I've turned IPSG on. There's a CLI command for it. So that shows you it's enabled, and so on and so forth. Now, this is the finale just to tell you as to how it all comes together in a host move. What we did till now is we looked at it piecemeal. We looked at dynamic ARP inspection and said, yes, it works after a host move. Then we looked at IP source guard, and we said, yes, it works after a host move. But then the control plane and the data plane don't exist separately, right? They need to come together when a host move happens. So the question is there a particular sequence in which this happens after a host move? So there is a sequence. So when a host moves from VTEP 1 to VTEP 2, this is the way it happens. Step 1, after the move, the host says that I have moved by sending one of the three things. It could be a ARP request to get the gateway MAC maybe. It could be a self-promotional activity by sending a gratuitous ARP, or it could be a reverse ARP. One of these things through which a host announces saying that, you know what, I've moved. First, dynamic ARP inspection has to kick in to ensure that the control plane is proper. Only after that am I going to enable the data plane for this particular user. And once it does, you will download the IPSG as well to hardware, and you're good to go. So with this, the control plane is sanitized, the data plane is sanitized, and host move is complete. Yeah, so this is what we want you to take away. The final thing is an aside point. Remember, we drew that box out there, the DHCP snooping database, with that lease also as part of it, the lease time. What is that lease time all about? We mentioned it briefly, saying that the lease time came from the DHCP server saying, thou shalt use the IP address for this duration. Yeah, why is that important? We saw that it was important because the host, if it needs to use the IP address for more time, it has to do an explicit renew, saying that I want to use it for more time, and the server allows it to use for more time. So that's the way it works. What if the host goes away, right? The host is gone. Then these DHCP snooping entries which are there on your VTEPs, what happens to those? We need to purge those entries so that they don't remain stale, right? How do we do that? We use the same lease time and do a countdown on each of the VTEPs to ensure that once it gets down to 0, and maybe the host is gone forever, then you decide to purge those entries so that they don't stay forever. So that's why you need the lease time in the DHCP snooping database as well. So what problems does that bring in? Lease time and VTEP addition. Remember the scale-out point that Tarique mentioned, saying that it is a fact as far as VXLAN is concerned. So that has to be taken into consideration here. So now we start with 2 VTEPs out there. Their respective DHCP snooping database is populated. And if you see that entry out there, it says 86,400 seconds, 24 hours. That means that the DHCP IP server, right, it gave permission to use that IP address for 24 hours. Now, after the DORA handshake happened, 12 hours have elapsed, right? 12 hours have elapsed. And so if you look at each of those VTEPs, what happens? They have the remaining lease time, which is what we wanted, right? We wanted those VTEPs to be in step so that it reads as remaining 12 hours. At this particular point, we decide 12 hours later after DORA, we decided to add a brand new VTEP. Why did we do that? Scale out, as Tarique mentioned. Now what happens? BGP EVPN route type 12 will come to our rescue in populating the entry, right? That's not a problem. The problem is that now you need to ensure that on this new VTEP as well, the lease time is not the total duration as given by the DHCP server. It should be the remaining lease time so that the entire fabric is in sync, right? You don't want this brand new VTEP having a lease time which is inflated. So for that reason, in BGP EVPN route type 12, we also pass in addition to the duration, a start time. And with that, we compute when a new VTEP comes in as to what the remainder time is and ensure that that is populated in this particular case. And what is the takeaway? VTEP addition, with this done, is successfully taken care. So these are all finer details that you face in a VXLAN context that you wouldn't have in a traditional network. The last point out here, guidelines. We saw this earlier. Remember to have DHCP snooping enabled as a precursor for DIE and IPSG. In fact, as the second point says, all the 3 features are complementary features. It doesn't make sense to turn one on and not the other. So for heaven's sake, turn on all the 3 features together so that you can have control plane protection, data plane protection, move protection, all that. Yeah, so that's why it says this is what complete first hop security is all about. These 3 features put together in a VXLAN context. With that done, I'll now pass the baton to Tarique. He'll talk about the data plane protection mechanisms and the control plane.
Thank you, Shankar, sorry. Right? He's very passionate about his feature because he helped build it. So now we're going to continue on with this theme of protecting the data plane. We ended with IP source card that was between the endpoint and the switch. Now we're going to talk data plane protection between switches. There are several data plane protection mechanisms we're going to cover today, and we're going to cover different security problems. right? Some can be related to confidentiality, some relate to integrity, some relate to availability of the system. So we'll start off with storm control. Then we'll move on to southbound loop detection, MACsec, and BGP EVPN RTBH in the context of VXLAN EVPN. Initially, when we thought that we're moving towards an IP-based fabric, we thought we would remove storms, but because of the L2 extensions that we can extend within the fabric and across sites even, we still have the problem of traffic storms that can occur. Let's look at an example. We have an attacker here who's in VLAN 10. The attacker does a flood attack. Now, what's an example of a flood attack? Well, you could send, broadcast frame, and you could even send lots and lots of frames with random destination MACs, right? That becomes unknown unicast. And what happens if I send lots of frames with random source MACs? Anyone can tell me if I'm blasting the MAC table with random source MACs, what will happen? Anyone? Anyone? Yes? Yes. Because why? The CAM table will get overwritten, right? Because the CAM table has limited resources, and as we're blasting the CAM table with more and more random source MACs, switches learn based on source MAC, it will override it. Then everything else gets flooded, as that gentleman said. So now we're flooding because we extended the L2 VNI within the site, and on the border gateway, which is my point of DC data center interconnect, we'll extend that layer 2 VXLAN tunnel across to the other site, and we've extended that same VLAN within site 2, and we have now essentially done is what? Extended our failure domain. Now the question is, how do we control this? In security, a lot of times what we try to do is we try to control the problem nearest to the source, right? So to prevent the problem, the damage that may occur, we try to contain it to one area. So now if we look at storm control, we have our traditional access interface storm control that we've had for a very long time in all our platforms, right? So we can do a storm control at the access layer near where the attacker is. But now, if you have a lot of bump traffic, broadcast, unknown unicast, multicast traffic, that can all aggregate at the border gateway point, right? It's an accumulation across many of the leaves, many of the endpoints, right? And if you're extending those VLANs across the site, then we can police that traffic, perform storm control at the fabric interface. The fabric interface is the link from the border gateway that connects to the internal site, and then the DCI interface. So when I'm referring to doing storm control on the border gateway, we call that EVPN storm control. So that's the first fundamental concept. EVPN storm control is only applied where? On the border gateway. We're controlling traffic, policing traffic that enters the fabric interface and then exits out to the DCI. And we will go into detail on how that works, including the mathematical formula of how the policing rate is calculated. I know you're thinking these Indian engineers, they always want to do math, right? Sorry, but I think it will help you understand how it works, right? It will help you work. Now let's look at the first example. Now the storm control at the access layer, we can do it using two methods. We can set a single threshold, right? So when that single threshold is exceeded for a particular type of bump traffic, then the corrective action will take place. The corrective action can be, by default, is to send an SNMP trap, or we can shut down the interface. So here you see an example, Ethernet 1.1. We're setting the storm control for unicast traffic level 40%, right? So that 40 represents the amount of unknown unicast traffic level on that interface. If it exceeds 40%, I'm going to send an SNMP trap. Now, for broadcast, we can, access interface, we can also set the units for packets per second. In this example, for broadcast traffic, we're setting it at 8,000 packets per second. So in this example, if 8,000 packets per second is exceeded for broadcast traffic, the action is, I'm going to send a trap. Now, let's look at the second example, which is we're going to set two levels, a sort of a minimum level, which is level 1, and then we also set a level 2. So in this example, you see, we first need, in order for you to use this feature, multi-threshold level, you need to first enable the feature, which is system storm control multi-threshold. You need to also carve out some TCAM space and reload the switch, right? Now, you notice here that for unicast traffic, we set it, the level 1 is 5%. The action, what is the action when 5% of the unicast traffic is exceeded? The action is to send a trap. Now, what happens when I exceed level 2, which is 10%? The corrective action is to shut down the interface. So quite straightforward. This is the easier example. The more complicated stuff happens on the border gateway. Because, A, we're dealing with different traffic types, broadcast, unknown unicast, multicast. And we're dealing with 2 interfaces. We're dealing with the fabric interface, right, which is traffic that's going to come from all my VTEPs through the spine to the border gateway, and then the traffic that leaves from one site to the other site. So we need to solve this problem at all those levels. So let's start off with the DCI interface. So here, imagine this box represents the border gateway, and then we have slice 0, and we have slice 1, we have the DCI interface, and we have the fabric interface. The first use case we're going to look at is traffic ingressing into the DCI. Now, the important thing for you to understand here is that policer on NXOS platform for EVPN storm control is only applied in the ingress direction per slice. You can consider the slice as to be the network processor that processes all the packets that are mapped to the specific interfaces. Okay? So now, we set what we call a storm control level, right? A policer level. Now, in this example, I set the policer level to be 10%. So what am I doing here is that I'm executing this command, EVPN storm control multicast level 10. Right? So that is essentially saying that on this border gateway, on the ingress interface for multicast traffic, the policing level is 10%. Now, how do I actually calculate the policer rate for the traffic, multicast traffic ingressing? The formula is the policer level, which in this case is 10%, multiplied by the DCI bandwidth per slice. So if we do the math, the policer rate for multicast traffic ingressing a DCI interface would be 10% of 10 gigabits. Here I'm looking at both of these slices happen to have one 10 gig interface on the DCI, so we get 1 gig. So what happens? 1 gig is the policer rate that is applied on the ingress of the DCI interface. Now what happens with broadcast traffic? Broadcast traffic, again, to keep the math simple, right? I did 10%. Again, the same similar command, EVPN storm control broadcast level 10%. Same formula we take to calculate the policer rate. We do policer level multiplied by the DCI bandwidth per slice. And again, we only have one 10 gig interface, so it's 10% times 10 gig, 1 gigabits per second. So this was the easiest example. We'll try to complicate it a little bit more, but what you see here is that for the multicast and the broadcast, the policer rate is 1 gigabits per second ingressing on the DCI interface. Now we'll look at the example where traffic is going to be leaving the site, right? So we're now going to apply it on the ingress of the fabric interface. Notice that on the fabric interface, on slice 0, we have Ethernet 2.1, 40 gig, while on slice 1, now we have 2 fabric interfaces, which are attached to Ethernet 2.2 and 2.3. They're all 40 gigs. The most fundamental concept you need to understand and remember is that on NXOS platforms, we do not do multicast policer on the ingress of the fabric interface. Can someone guess why we decided to do that, maybe? Anyone? What do we use multicast for within the site sometimes, and the underlay for? What's its main function? to handle bump traffic, right? So bump traffic that needs to go within the site. Now, if it hits one of my border gateways, also becomes a member of that underlay group. I don't want to accidentally rate limit ARP traffic maybe that was supposed to go across the site, within the site, right? Resolutions. So to avoid that kind of impact, unnecessary impact, we decided that we will not do multicast policing on the fabric interface. So now in this example, we want to now police the broadcast storm control traffic. Again, it's the same command, EVPN storm control broadcast level 10. But the formula is a little bit different, right? Don't worry, it's not that complicated, okay? Let's just go through it. So you have the policer level, 10%. Then we have the total fabric bandwidth. So we're looking at slice 0 is here, total fabric bandwidth, 40 gigabits per second, right? Now, then we go to total fabric bandwidth. That is what? That's the total fabric bandwidth that we have across all the slices. So 40 times 3 is 120. But look at this. We have to consider also the DCI bandwidth. Why? Because what happens? A lot of times the DCI bandwidth is not as much as the bandwidth available within our site. So we can't overwhelm the DCI bandwidth, right? We don't want to oversubscribe the DCI. So that's why we have to take into consideration the DCI bandwidth in our calculation for the fabric interface policing rate. So the broadcast policer becomes 0.66 gigabits per second inbound for broadcast traffic. Now, what happens in slice 1? Now, notice the difference between slice 1 and slice 2. Slice 1 has double the fabric interface. So what would you expect? The policer rate will increase proportionally for that slice, and that's what exactly you see here. The only difference you see is what? The slice 0 only has one 40 gig interface. The slice 1 has two 40 gig interfaces. That's how we got 80 gigs for the fabric bandwidth for that slice, and therefore proportionally the policing rate increased. Right, so now the broadcast policer is also applied for slice 1 at 1.3 gigabits per second. The same principle is applied for unknown unicast. So how do you verify it? Show forwarding, distribution, internal EVPN, storm control. So you see there, you see it by the, you see the policer rate level by the traffic type, and then you see the total bandwidth across the DCI and the fabric interface. Now, the show hardware VXLAN storm control, it actually shows you the results for all that math I showed you earlier, right? It's a long output. It shows it for each slice, for each interface and everything. So if you're interested, you can look into that show command. Sorry, this clicker. Okay, now we'll move on to southbound loop detection, right? So we looked at methodologies to contain our storms. Now let's look at southbound loop detections. Now, with the VTAP, yes, northbound on the fabric interface, we have layer 3 interfaces. But now, southbound, you could connect a layer 2 network. Now, some people may actually mistakenly do a loopback cable. That happens, right? And in that scenario, what will happen? If you allow that same VLAN on that loopback connection and extended that same VLAN over VXLAN and some sort of broadcast traffic is sent, you will have a looped path, a looped condition. Then we have external device loop path. Now, by the way, this could be by intention. That was maybe unintentional, the first example. But the second example could be by design. We may have a bridged firewall, a transparent firewall, or someone connects some other layer 2 switches to the VTAPs, and then what happens? You have a possibility of having a loop path, right? Then the last part, the last example is, hey, I have my legacy data center, I have my VXLAN EVPN, I'm doing L2 extension between them, right? I can do a VPC based, right? Or maybe I've done a connection, or maybe I could even make it a bit more complex. I could have 2 data center sites. I was initially using a legacy DCI like MPLS L2 VPN. Then I decided I'm going to use multi-site VXLAN EVPN. I extended the same VLANs across both of them. I forgot to decommission it from the old one, right? So those things happen. I'm sure you guys have hit it. So now the thing is, how do we deal with it? Now, since we've already connected everything and we made the configuration mistake, I should at least be able to detect the loop, right? And then take corrective action. And that's the purpose of southbound loop detection. The goal is to detect the loop, not prevent the loop. The loop has already occurred. And what do we use? We use old tools from the box that we always have, right? Every time you want to solve a problem in networking, you use BGP, right? You take something from somewhere else and put it over. So in MPLS L2 VPNs, we used to have the CFM packets, Connectivity Fault Management Packet, commands like, traceroute MPLS, things like that, right? So we use the same kind of concept, and we bring a frame based on the IEEE 802.1 AG standard, which is the CCM frame. Basically, it's a probe. So if you see this example, the Leaf 1 will send a probe, a CCM probe, and it's going to be sent per VLAN. And it's only going to be sent for the VLAN that's mapped to an L2 VNI, okay? Only for a VLAN that's mapped to an L2 VNI. And then it will go southbound. This CCM frame will have a specific reserved destination multicast address that the Cisco switches know that, this is a CCM frame. I need to forward it onto my peer switch. And it sends it over. It's received on Leaf 2. Leaf 2 is like, oh, okay, I received it on this VLAN. It's mapped to this VNI. It's extended. Let me send it out my NV interface. It goes across and comes back. So now the probe says, oh, Leaf 1 says I've detected a loop. Now what do I do? Okay, I need to block that VLAN on my southbound interface. Block the VLAN, not the interface. So the other VLANs where the loop is not detected will not be brought down. Right? And then, as you know, whenever loops occur in a bridge network, right, it's occurring, it corrupts the MAC address table, right? The MAC address table may be mapping to the wrong outbound port. So then we need to flush my local MAC table, and I'm going to send a MAC flush message down southbound to switch 1 and switch 2 and say, please flush your MAC address table. There's been a loop here. Everyone flush your MAC address table. Then what happens is that port recovery time starts, right? And then when the port recovery time starts, and if the CCM loop is received again, then it's like, okay, we continue into this state. But then if it's not received, it's going to wait for another port recovery time and then bring up, you can either manually bring it up, or you can set up an error disable recovery time, right? The same tool that we use for like BPDU guard and things like that, same thing. So now that is how this feature works. How do we configure it? So like any feature in NXOS, you got to do feature NGOM VPN, NGOM. Now, what does NGOM stand for? Next Generation Operation Administration Management. Basically, it's the suite of connectivity testing features that we created for VXLAN, like Path NVE, right? Ping NVE. So that comes under that suite of features. We do NGOM loop detection. Now we can set the periodic probe interval, which is 200. That's the time, the interval I'm going to send the CCM probe. Then I'm going to also set the recovery time. By default, it's 10 minutes. So it's going to wait 10 minutes. Once it blocks the VLAN southbound, oh, I didn't receive a CCM. Let me wait another 10 minutes just in case another loop comes. Then boom, okay, now you can come up. Or you can, now that you're sure that you told, Harry, that why did you connect those two cables, remove them? Okay, let's bring it up now, right? And then you can view the history and status of a port. So here you see show NGOM loop detection status. VLAN ID is 1000. Ethernet 140 is that southbound port, and it's in the block state. Yes? Sure. Great question. Great question. So the question was, those southbound switches, can they be non-Cisco switches? Now, unfortunately, they can't, right? Because that destination MAC address that we've set on the CCM probe is Cisco, only the Cisco switches will understand it. Okay. Any other questions? Guys, no question is too basic, okay? Yes? Okay. Yes, so the question was, from what I understood, that both leaf 1 and leaf 2 can send the probe, right? So what and so how do we prevent loops in both directions, right?
We can block totally the L2 domain if we have two probes from leaf 1 and leaf 2.
Right. So, okay. So if we go back to the previous diagram quickly. So in this, the question I believe was asked that now if leaf 1 can send a probe southbound, right? And leaf 2 can also send a probe southbound, the same probe, right? In both directions, right? So, could you repeat the second part of the question?
That time we can probe totally L2 domain on the southbound part.
Why do you say it'll break the?
Because the leaf 1, which CCN message, will block the port to
Yes,
legacy system.
100% right.
And that can happen in the same time on leaf 2.
Yes, and that is the intention. So now I understand the question. I'm sorry, I understand. So he's saying that in the event so now for a particular VLAN, on leaf 1 and leaf 2, we're extending those VLANs, right? And both of them will be sending the probe, right? Now now both sides, when they detect that a loop condition has occurred, both sides will then shut down that VLAN on the interface, and we have brought down essentially the looped path. That's the very intention of this feature. We want to prevent the storm from going indefinitely in the system. So we'll cut off half of the layer 2 path. We cut the loop from the bottom. Not all the traffic, only for the VLAN for which the probe was sent. Yes, it's a CCM probe per VLAN. So we do not shut down the interface. We block the VLAN. We shut down the VLAN only, not the interface. Yeah, we isolate it. Yes. The side that detects the loop first will shut down the VLAN on southbound, right? And then the other path could be available. Right? Yeah. Now, if in the same time leaf 2 detects, then we shut down both. We cut the loop path. Remember, the intention is just to detect a loop path and break it. Yes. Yes, it will. 10 minutes, yes. Or you can manually bring it up. Okay, sorry, I have to proceed to the next topic. I hope I've answered your question, right? So now MACsec. This is a complicated topic because, like everything in security, there's math underneath the hood, right? There's a lot happening. I will try to simplify it for you. So let's look at an example. Let's look at the problem state. The problem is that we want to be able to send securely traffic from our greenfield VXLAN data center to my legacy data center. Maybe my file server, my database is still located in my legacy data center, but I've only moved my app over. But I want to now, upload some file. I want to access my database. I want to be able to do it securely as the data is transiting. So now what problem in security are we solving here? Confidentiality, right? Whatever confidentiality kicks in, we are going to deal with encryption. We are going to secure the data in transit. So what we use here is MACsec. MACsec is an IEEE 802.1 AE standard. We're encrypting at the data link layer. So what does that first tell you? Oh, we're encrypting at data link layer. Does it matter what layer 3 transport I run on top? MPLS, VXLAN, anything, right? Doesn't matter. It will all be encrypted. Now, how does the encryption process actually work? Well, I'm assuming here that the server sends in clear text to the switch. By the way, MACsec can go all the way to the NIC card of the server. But in this because we're talking here on Nexus, I'm only going to talk about switches, right? So what does the switch do? It will receive it, leaf 1 encrypts it, sends it over to spine 2. Spine 2 will decrypt it in the ingress, then and as it transits through spine 2, notice it's in the clear. What does that tell you? Oh, it's in clear. Maybe I can do some processing, set QoS, classify it, right? I can maybe do some deep packet inspection. It's not encrypted anymore, okay? Then it will re-encrypt it and send it across to the next hop device and then eventually get to the server 2. So what is MACsec providing? It's providing confidentiality, which is encrypting the traffic as it transits, replay protection, so it protects us from man-in-the-middle attack, and it provides us data integrity. No one has changed it, hampered it, played with it while it is in transit. Now the question is, well, last thing I want to say is, why would you want to use MACsec over IPsec, let's say? All of us have heard of IPsec, right? Anyone want to tell me why you would want to use MACsec over IPsec? Any advantage from your experience? Yes, MACsec is done, as I said, port level, right? Port speed level and physical layer. Now, IPsec, we always have an ASIC engine, some form of ASIC engine, and it always has some sort of scale limitation, number of sessions you can encrypt, right? So that becomes a sort of a bottleneck for some systems. So a lot of times we go with IPsec, but I'm not saying IPsec and MACsec is better than IPsec. I'm not saying that, okay? But I'm saying IPsec has its place, MACsec has its place, right? Now, remember, MACsec only works over Ethernet, right? And now Ethernet is dominant everywhere now, pretty much, right? It's LAN, WAN, all that stuff. But, you know, if you don't have an Ethernet transport for some reason that can support MACsec, then you can do IPsec, right? So one doesn't replace the other. Then MACsec header, essentially we just add a MACsec header. It's sometimes known as security tag. And then we add the ICV, which is the integrity check value field. Now, like IPsec, we have the, in IPsec we have ISA, KMP, right? Phase 1, phase 2. What is all that doing at the end? I'm going to simplify everything for you, right? This gets quite complicated, but I'm doing it in the simple way, which is, okay, we're going to first set up a pre-shared key, right? And then what is the purpose of that pre-shared key? It's to identify each node, right, point to point. Then we're going to bring up one of the nodes is going to become what we call the master role. The job of the master is, hey, I'm going to start exchanging my key to you. You send your key to me, and then we're going to have we're going to bring up a secure session. Now, what's the purpose of bringing up the secure session? To exchange keys that we're going to actually use to do the encryption. And I'm going to go over with you all the keys at a very high level. Now, once we have the keys, we can now exchange data, encrypted data. And hey, we need to maintain our session so we keep alive between each other. Now, what are these keys? All right, you can do a PhD thesis on these keys, but I just want to do a simple one high level. So now, a user configures a pre-shared key on the Nexus switch. Now, by the way, these pre-shared keys can come from external servers. We have master key servers, things like that. Now, this pre-shared key actually becomes what we call from this pre-shared key, we derive what we call a connectivity association key, right? And then basically, what this CAK is it's a seed key. And then there's some math that's done, magic done underneath the hood, so that from this CAK, we derive 3 keys. First, we have the SAK, Security Association Key. In simple English, the role of this key is to encrypt the data that we're going to send. Now, it's important to keep the key that we use to encrypt the data secure. So therefore, we create another key that's going to encrypt the key that we use to encrypt the data. That key is called the key encryption key, right? And then finally, we have the ICK, integrity check key. That's sort of the key that we use with our hashing algorithm to make sure that the data has not been modified. Okay, guys, so just to tell you at a high level, this is how these are the keys that are exchanged and what are their use in MACsec. Now, how do you configure it? Luckily, the configuration part is very easy, right? It's very easy. If we enable the MACsec, then we create the keychain, right? So number one, enable the feature. Then you create the keychain, right? Now the keychain, notice I put key CKN. Now what's CKN? It's not another type of key. It's the value that we use to identify the CAK. Remember what's the CAK? That's the key that we use to create all the other keys, right? And then what do? I specify the CAK. It's an octet string value, and I identify the algorithm that I'm going to use to encrypt and exchange this CAK with my peer. Then after that, I can set other parameters. What's my send lifetime, receive validity of the key. Then finally, I need to now configure what we call the MACsec policy. And the role of the MACsec policy is actually to define what encryption are we going to use to encrypt the actual data. So these are our cipher suites that we use, AES standard. And we can do other things like, hey, what's my priority level? If you're the lower the priority, I'm going to be the master, and I'm going to start negotiating with you. Or I can also set the SA key expiry time. Pop quiz, what's the SA key used for? 3, 2, 1. Data encryption, right? It's used for the data encryption. And then finally, I go on the interface, and I say MACsec keychain, and give it the policy name, right? We apply the policy with the keychain. So that is a 10,000-foot view of MACsec, right? What it's used for, right? Now we're going to solve our second to last problem, which is denial of service attacks in our network, right? Now we know that it is one of the oldest enemies in networking. It, till today, is bringing down like AWS, right? We're having some sort of DNS attack, something. So we need to defend ourselves from these things. So let's look at it in the context of VXLAN EVPN. The attacker can exist anywhere, right? It can be within my site. It can be connected to my border leaf. It can even be coming from another data center, VXLAN data center. So what's the goal of a DOS attack? There's a victim that we want to attack. There's a victim that we want to attack. And what's our purpose of attacking this victim? Overwhelming it. I could be overwhelming you with a lot of information right now. I apologize. This is not a DOS attack, okay? Right now, I'm overwhelming this system so that I remove its availability. You can't access the system anymore. And now if you can't access the system, what happens? No connectivity, no availability. You've succeeded. You've created damage, right? So now we have a victim. This victim is being bombarded from all sides, right? It's coming from attacker 1, attacker 2, and then attacker 3. They're all coming. They're all attacking the system. And as collateral damage, what happens? Links, right, in the network will also get oversubscribed, overwhelmed. And you will start dropping traffic for legitimate traffic also, right? Host 1 here, traffic is a non-victim, but it will also get impacted. So now, what is this? How do we solve this problem? We need to first identify the victim, right? And that an attack is being performed. I don't go over that in this presentation, but we can use NetFlow, SFlow, some monitoring tool, something, right? Some sort of monitoring tool to detect that, okay, there's some sort of attack happening. There's a huge increase in the traffic towards one destination. Now, then what we need to do is, hey, if I somehow distribute a route, now it's for bridge traffic, I would say maybe if I was able to program into the CAM table, any traffic going to this MAC address, drop it. Or in the routing table, I could say any traffic going to this IP or going to this network, I send it to null 0. Null 0 is a logical interface, right? It doesn't process it any further. So what does it do? It becomes a bucket. It's a bucket to dump. If I could just somehow distribute that everywhere, I can then save this. I can drop all traffic to this destination. But what's the side effect of that? I drop all traffic to this destination to save the rest of the network. Right? So this is what we call destination-based RTBH, right? Destination-based. We are going to drop traffic to the victim, all traffic, across the network to save the network. So how do we create these drop entries? Now, in EVPN, remember, it's Ethernet VPN. It's integrated routing and bridging. So I need to take care of both cases. I need to take care of the case for bridge traffic, right? So that is traffic within the same L2 VNI. Then I'm going to refer to the MAC table. So how do I add an entry in the MAC table to drop traffic to the victim? So I do MAC address table static. I give the MAC, VLAN 5, drop. Right? So all traffic destined to this MAC will be dropped on the device that has this entry in the MAC address table. Now, what if it's routed to a host IP? Right? Routed to a host IP. Then in NXOS platform, there's a requirement that you need to add an ARP entry. Now remember, ARP table is a mapping table, right? It's not a forwarding table per se, where you have an action, set it outbound this interface. So now I need to take that MAC table, the MAC address from the ARP table with that IP, and then put an action drop in the MAC table. That correlation is done in the back end. So anything destined to this IP 10111 is dropped. And lastly, we have the example of a network being attacked. We do an entry pointing to null 0. So that will drop all traffic going to this particular network. So now you may ask, how does this, okay, I get it, you're adding like these entries to drop, right? Where do I do it, right? Where do I apply this, and how does it distribute across the whole network, right? So I'm going to give you the view. So what happens, I'm going to first find a trigger VTEP. So consider trigger VTEP, the VTEP where you've applied this static route to drop the packet because you identified the victim. You identified the victim using some tooling, right? Okay, the victim is attached to VTEP 1. Then you manually add that drop entry. I'll show you in a configuration example. Then what happens, once I add that drop entry, BGP EVPN on the Nexus platform will see it, and through type 2 and type 5 route, add a black hole community. There's a well-known black hole community, right? And when it advertises that MAC or host IP or prefix, it attaches that community. And when the other route, when the other remote devices, like for example, the border leaf, the border gateways, receives it, that advertisement with the well-known community, it's going to program into its routing table automatically or MAC table that drop entry. So we create that's what we call it, the trigger VTEP. We apply the drop route on one side, then via EVPN using black hole community, we signal to everybody else that, hey, this guy or this MAC address or this IP is getting attacked. We need to black hole this traffic, right? So that's what essentially how we're solving the problem. Yes? Sorry? Yes. Yes, but what we do is we sacrifice one to save all. You get it? We're not saving the whole everybody. We sacrifice one to save all. Right? That's what we do. That's why we call it the victim. Right? We isolate the victim, right, completely to save. Now the better method, that's a very good question. The better method would be what? You black hole traffic coming from the source. Yes, but here I only gave the example for destination. All right, but that's a very good question. Thank you for that. So what does the config look like? So basically, the config looks like something like this. So on the trigger VTEP, right, on the trigger VTEP, I apply this config, the drop entry. I'm giving you one example with a destination IP host, a destination host being attacked. Then what happens? On the remaining devices, I do need to apply one route map, though. The route map, basically, what it does is first on the top, you see I have a community list that matches black hole community, right? And then on the route map, I match that community list, which matches the black hole, any route with that black hole community, and I set the weight to 65,535. Then what do? I use this route map on these VTEPs inbound to my spine in my EVPN peering. So when I receive the routes from the trigger VTEP, oh, it's got the black hole community, install it, it's going to have the highest preference, and I'm going to now start black holing traffic to this victim. That's all it is. It's a simple mechanism. So we took, we borrowed concepts from MPLS MVPN and just applied it here, and we used the standard black hole community to signal the programming of these null routes. So I have one last topic. If you can just stay with me for 2 more minutes, if that's okay. Control plane protection, right? Basic topic. Now we need to protect our control plane, and control planes can get attacked intentionally or unintentionally. A large routing update comes from the border leaf to the border leaf device. If you don't have the right protection mechanisms, right? I mean, imagine an entire internet routing table coming accidentally to a border leaf that wasn't designed, doesn't have the routing profile to use and take care of such large-scale routing. Now, with the control plane policing, it's important for you to understand the punting path, right? So what happens is that, for example, an ARP request comes to a switch, it comes to an ingress forwarding ASIC. What does the ASIC do? It will punt it up to the in-band driver through the COP component per module. A lot of people think the COP runs on the supervisor. It doesn't, right? On a modular platform, the hardware rate limiter, the COP, they all run on the modules, right? Then it goes through that process, then it gets punted to the supervisor. So that's basically the punt path. Now with control plane policing, in NXOS, we have 4 COP profiles: strict, dense, moderate, lenient. Now, as the names imply, strict means what? I'm going to have a lower policing rate, right? I'm going to drop faster. But lenient means what? I'm going to have a higher CIR or policing rate. So I'm more lenient. I'm going to let more traffic come to the CPU. The default is strict, right? But for some people, you don't want to have this Cisco custom profile. Strict profile. You can create your custom profile. And the way we create the custom profile, you copy the profiles that are there, give it a new name, and then you can modify it. By default, I believe there are 25 class maps. You can even change that, add your own. So what does the profile content look like? You have first an access list. Access list is what? The purpose of the access list is what traffic do I care about, right? What traffic do I care about that gets punted to the COP? Then I'm going to take those groups of traffic that need to be treated in the same way. I'm going to put them in the class map, right? So here you see I match access group, I match the access list, and I put it under the class map normal DHCP. Then what do? I use that class map within the policy map to set my action. The COP is able to do 2 things: police, and it can also reset your QoS value to give it a lesser priority. That's the main difference between COP and hardware rate limiter. Hardware rate limiter can only police, right? While the COP can do the other action. So we then take this policy map and we can apply it on our control plane. Now, how do you view a policy? You do show policy map control plane. Here are 2 interesting things I want to call out to you. You notice that I said the cost level 1 is the lower priority, right? And cost level 7 is higher priority. What do you see with cost level 7? Cost level 7 in Nexus is our no-drop queue. It's our highest priority queue. So then you notice that the CIR is 36,000, while for cost 1 it's 800, right? So we have a higher CIR for higher priority traffic because we want to avoid dropping it, all right? We want to avoid dropping it. So lastly, how do you actually view that drops are happening on the control plane? Show policy map interface control plane. You see the conformed ones are not the ones that are being dropped. The violation drops are the ones that are being dropped. So in conclusion, you need to make sure that you build the security of your infrastructure from the foundational level, right? Let's get our switches hardened first. When we're looking at VXLAN EVPN network, we need to look at our underlay, we need to look at our overlays, right? And put these mechanisms that we already have natively on the switches to harden them. We went over several of them, and I thank you today for attending our session. Please do the survey. You will get a free T-shirt, I believe. I believe it's Armani, or possibly, I don't know what it is, right? Whatever it is, I wish I could get a shirt like that, but I wish you all the best, safe journeys home, and thank you for your time.